Welcome back to another episode of Dave Does Math from Home. We have a good one for you today. Today we are talking about volumes of rotation, which is an extremely good time. Everyone loves it. It's everyone's favorite. But before we start doing volumes of rotation, I want to do a quick little review of integration and the connection between integrals and area. And then we can use that as a starting off point to get to volumes of rotation. So let's just do a pretty accessible example. We'll start with y equals the square root of x. That looks like this, more or less. And let's say we want the area beneath y between x equals 0 and we'll go to x equals 9. So here's 9, here's 0. We're going to get this area. So, of course, we all remember that the way to get this area is we take an integral from 0 to 9 of square root x dx. And before we actually start doing this integral, I want to talk about what this integral means and where it comes from. Remember that the big squirrely s kind of means sum. It's like a big infinite sum. Usually the symbol for sum in mathematics is the Greek letter sigma. Kind of looks like a big sharp E. But when you're doing a sum with infinitely many things, and all of those are infinitely small, you use the squirrely s for an integral. And these pieces right here are what happens when we cut this area into little strips vertically. And then we look at these things as rectangles. So this distance, the width of each of these rectangles, is dx. That's a tiny, tiny, tiny little slice of the x-axis, infinitesimally small. And that's this. And this distance right here is the height. And that's always f of x, or in our case, the square root of x. So, when we multiply the height and the width together, we get the area of one single rectangle. And then the big squirrely s thing is what takes the sum of all of those rectangles between 0 and 9, and that's what gives us the total area. And that's what all of this means. And then if you actually want to do the math on it, the math is pretty simple. This is 2/3 x to the 3/2, evaluated at 0 and 9, which is 2/3 of 9 to the 3/2 minus 0, which is 9 to the 3/2 should be 27, so this should be 18. 18 is the area. Once you get this thing set up, we all know how to actually take the integral and evaluate the integral. That's the easy part. Getting this set up is what's going to be really interesting for the section we're about to start, because we're about to make things much more difficult. We're not going to be dealing with rectangles anymore. We're leaving rectangles behind. But keep in mind that this is the sum, and this is an area. So, with that in mind, let's do something more interesting. I'm going to take the exact same function, y equals square root x. Same function, looks the same, does this. I'm going to go on the same interval, 0 to 9. Here's what's different. This time, I don't want the area. This time I'm going to take this function I'm going to spin it around the x-axis to create a three-dimensional shape, something sort of round. So when I spin it all the way around like this, there'll be a part down here, and it'll be a three-dimensional thing. I like to think of this particular shape as kind of like a bullet bill. There you go. We get a three-dimensional shape, a solid, it's round, it's vaguely bullet billish. So today's plan is, I want the volume of bullet bill. We can find that. And the process of finding this volume is going to work, in theory, a lot like the process of finding the area in the last problem. We're still going to take this thing and we're going to slice it into infinitely small little pieces. The big difference is, now, instead of finding the area of this piece, I'm going to take this piece and I'm going to spin it around the x-axis. And when I spin that rectangle around the x-axis, it's going to create a thin little disc. I don't know if any of you are old enough to remember what CDs are, but it's kind of like a little CD or a DVD. Oh, I guess, yeah, you have Blu-rays, right? Amazon Prime hasn't completely destroyed the Blu-ray market. Yeah, there's like red boxes in the grocery store still. It hasn't, I mean, at the time of recording at least. I don't know when you're watching this. But yeah, so you take a really, really, really thin strip of something, you spin it around the axis, you get a really thin disc. And so, just like in the last problem, we took a bunch of really thin rectangles, we found the area of those rectangles, and we added them all up using an integral. In this problem, we're going to take this little rectangle, we're going to spin it, turn it into a disc. We're going to find the area of that disc, and then we're going to use the integral to add up all those, I'm sorry, not the area of the disc, that's foolish. We're going to find the volume of the disc. Discs are three-dimensional shapes. We'll find the volume of the disc, and then we'll use an integral to add up all of those volumes together to create the total volume of the entire shape. So the first thing we need to do is, we're going to use discs, so we need to know the volume of a disc. A disc is a kind of a cylinder. It's just a, I mean, normally when we think of cylinders, we think of things like, you know, water bottles or like soup cans, right? They're a lot taller than they are wide. But geometrically, this disc has the same sort of basic shape. It's just really, really wide and really, 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 really flat. So we tend to think of them more as circles than cylinders. But it is technically a cylinder, and that means that the volume is pi r squared h. So we need to figure out what r is, the radius of the cylinder, and we need to figure out what h is, the height of the cylinder, and these are things that we are all capable of doing. The radius, because we're spinning it this way, this dimension is going to be the radius. This distance is a y value, and that's going to be the square root of x. So the radius here is root x. The height of my cylinder is going to be this distance right here. And that tiny, tiny little infinitesimally small, extremely thin chunk of the x-axis is still called dx. So that's our height. So we have our radius and we have our height. So the volume of our disk, if we put all this together, is going to be pi times root x squared times dx, which simplifies into pi x dx. This is the volume of one disk. And it varies across this range. Close Over here it's going to be really small. Over here it's going to be really big. We need a way to add all of these volumes together. And we have that. It's the integral. The volume of bullet bill is going to be the sum from 0 to 9 of all of these disks, pi x dx. Pi, of course, is a coefficient, so it's safe. We can pull that on the outside. So that's a nice change. So now all we have to actually integrate here is x dx, which is really simple to integrate. We know how to do this. This is pi times x squared over 2 from 0 to 9, which is 80 pi times 81 halves minus 0 halves. So we get 81 pi halves. That's the volume of bullet bill. I'm sure knowing this is a great weight off your mind next time you're playing Super Mario Bros. 3 for the Nintendo Entertainment System. Every time a bullet bill comes at you, you can be like, I know how to find that thing's volume. It's 81 halves pi. There's more to come. Stay tuned.